Could someone close the door, but leave the door stop in between the door and the jamb so people can get in? All right, good. So I'll go ahead and get started. Let's see, a couple of things before we get into the lecture. We're slowly but surely getting all of our infrastructure up. Piazza site is working. If you have not gotten an invitation for it and you're enrolled in this class, please send email to Max, because it is an invitation-only thing, and it turns out that there's at least one aspect of it that it needs to be that way. So there's also a class website. So it has my email. So it's on the institutional computing site at instructional computing site at EECS. Has my name, my email, Max's name, Max's email. The main thing, though, the important thing, is that the lectures are posted there. I will, as I said, I will attempt to post the lecture every morning before class starts, possibly even the night before, so that people can download the lecture and kind of follow along or make notes on it or whatever. So lecture 3 is what we're doing today if you want to download that. Now, that said, the lectures, I reserve the right to, at the last minute, make editing changes. I will always post the revised lecture after class. So what else? I guess another important point here is the kind of getting ourselves set up for the Git repository access. Max has given us all an assignment. I was given it too, was to generate an SSH key and send him the public key. So I hope you've done that. If you're having trouble with it, get in touch with us. One important thing is that turns out this is not my day job. I have a day job up at LBL that occasionally will require me to miss class. So what I plan on doing for that is, first of all, announce it in advance. Secondly, classes that I miss, I will give makeup lectures, and I've already decided how I'm going to handle that, is that I will schedule a lecture for the time slot before this, because this room is available from 9:30 to 11 generally. And I will find a time slot, give the makeup, and then proceed to the next lecture. Since these lectures are all being videotaped, it's not obviously far from essential for people to show up, although I'd really prefer to have at least a few people come and see me in person, because lecturing to an empty room is kind of a little weird. And as is the use of videotape, there is no tape. It's just bits. I will give you a tentative heads up. The first lecture I will have to miss is probably going to be the 14th of September. I will, when I am firm on that, which will be in the next day or so, I'll let you know. I'll let you know for sure. All right. So I believe that's it for administration. Any questions on this? All right, good. So let's go into the lecture. So today we're going to talk about C++, the real thing, as opposed to the C subset. C++ is a huge language, but at its heart, it's C, and it adds, from kind of conceptually, only is adding a relatively small number of things as kind of core language features. And then there's a bunch of stuff that gets added as libraries, that gets added as various sorts of syntactic exotica that mostly you won't have to deal with. So First, I'm going to talk about a couple of things that could have been in the C type system, except they would be trivial in the C language, but in C++ they become essential. And those are reference variables and consts. Then I'll get to the heart of the matter, which is to take you through in a fairly leisurely fashion the idea behind classes. Classes are user-defined types. Then the other big thing that is very useful in C++ is templates, which are types that are parameterized by other types. What does that phrase mean? You'll see shortly, but I'll give you a hint. If you have an array, something that you'd like to have as being kind of the parameter in that type definition of an array is what the type of the value is. You can have arrays of floats, of doubles, of ints, of pointers to pointers, and they share a lot of implementation when you have arrays. So for array and for lots of other things. So we will be talking about how the basics of templates works. And then, of course, here's one of those things marked in green, and I will try to avoid mixing red and green for the 15% of the males in the room that are colorblind. So it'll either be red or green, but very rarely both. The standard template library. This is something you should look at online. Wikipedia is a good place to start. And we will talk about that here as well. So what are references? They're closely related to pointers. So in some sense, they're a dual to pointer, but not quite, because they're kind of single assignment objects. They directly reference another object of the same type. So one way of saying this, at least at the level of programs you would write in C, is that it's a way of renaming something, and you can only do it once per scope. So if you have, so here's the kind of the sort of thing that you can do. Let's see if I can do this. Is that if you've declared something to be a reference to, there's declared something to be an int, k, you can declare the variable ref to be a reference. So ref is a reference to an integer. And you can declare it to, so you declare it and at the same time you define it. That's how refs work. You cannot declare and then separately define. And they can only be defined once within a scope. So we've now given k another name. It's called now, you can refer to ref, and it's the same as referring to k. Now, why would you ever want to do this? Well, I'll give you some silly, but not actually all that silly reasons for doing it. Let's say you have some complicated array structure that you want to just index as kind of as an array. But actually, the arrays have names. So in doing gas dynamics, I have something that's indexed from 0 to 5. But they actually have names. They're mass, 3 components of momentum, and energy. And I'd like to use those names in those calculations because I can see what I'm doing. And consequently, I'll make reference variables. It doesn't cost me anything because they know, the compiler knows that these are really the same object. You've just renamed them. There are some special things about references that you'll see in a little bit about how they are used in connection with classes. So they're viewed in some vague way as being dual to pointers. A pointer is declared using the symbol for dereference operator, star. A reference is used for the symbol of taking the address. Well, ref is not an address. It is actually, it's its own thing. But in some ways, it will act as if it is what you're passing around is the address. So here's an example, a little program with references in it. I've declared a pointer to an int. I've declared an actual int, k, and then I've given it another name. I've declared a ref that is equal, and I set it equal to k. And then I set the pointer to be the address of k. Now I've done all that, and then finally I set k equal to 2. and I print out what's k, what's each of these variables, and what is it pointing at. And here's part of the surprise. K has the value 2, not surprising, and it's stored at that memory location. Pointer points to the value 2, stored at the same memory location as k. That's familiar to us. That's what happens when we set pointer to the address of k. Ref has the value 2, not so surprising, but here's the part that kind of gives away the game with respect to what ref is. It's, when you ask what its address is, it is the same as the address that you're pointing to. So you're really just renaming. You're not creating a new variable. And so it has the same address, it has the same value, it is just another name. And as you will see shortly, important for functions. So the const qualifier is something that tells us when you can't change something. So if you declare const int, for example, const int j equal 1, that means j cannot be changed later in the defining scope. The const qualifier aids the programmer in understanding the code. J is known to be 1 everywhere in the current scope, and you can't mistakenly change it later. Const is it's a const qualifier. It sounds like it's kind of something that's festooned on top of things in an ad hoc way. It isn't. It's actually part of the type system, just in the same way as you have different variants on integers, long, 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 etc. Const int is a different type than int. It's related to int, but it is treated differently by the compiler. So for example, you get a compiler error I think you will get a compiler error if you had this here followed by trying to reassign j. J's const. Now we go through a bunch of things here, and I'm not sure how much value it is in walking through these kind of one by one. But I will show you one that's perhaps when you have const ints and pointers, or const a type and a pointer. So when you have const int, the pointer is pointing to a const int. That's legal. So you know that the contents of the pointer cannot be changed. It can only be, and it's only allowed to be pointing at constants. On the other hand, if you have a int star const pointer, that says, so how do we have this? So this is, see, I can easily, I'm sorry, I have it backwards. Const int star pointer, that says that that star pointer, the address cannot be changed. We can change what pointer it points to, but the address can't be changed. Here it's the other way around, is that the pointer is a const, okay, let me table this one. I've got myself wrapped around the axle with these things. Now, if you put in enough consts, nothing can be changed. You have a const int and a const int star const pointer, so the pointer is const, and what it points to is const. So let's just skip over that. Using references and const, the place where you see it useful is in function calls. So we have a find Vmax, which is given an array, find its maximum value, and find its location. So what we're doing is that the maximum value is going to be the return value. That's the float. The input is a set of an array of floats. There's another input, which is the length of the array. and then there is an input which is a constant. Now, these two are not inputs, they are not values, they are references. So this is the mechanism by which you get what's known in other languages as call by reference. When you pass in a reference to a variable, one way of thinking of it is that site will get modified. That's different from call by value. Call by value, you pass in values, they get copied, they're only defined in local scope, and they go away after you exit the function. This is a way of passing variables out through the argument list. That's what reference variables, reference variables are good for. Now, what's const good for? Well, these two guys, you're saying you can't do anything to length or to the array that would destroy its constness. So you're not allowed to, there's a question of what that means when you have a pointer, and that's what passing in a float of v bracket is. If that were a pointer, if that instead were const float v square bracket, instead it was const float star v, what it says, you can't change the pointer. So you know it's going to say the same array that you started with. Const int length, that's a little less ambiguous. You're not allowed to change whatever that value is, because these things are getting passed back out. In principle, they could get changed by the function. Here you're saying, no, these things are not allowed to be changed. And in fact, the compiler, if you attempt to change them, will catch you at it and say, that's an error. Now, v has not been changed. Length has not been changed. If you look at, we're computing where the max is, we figure out what the location is, we figure out what the value is, we return the value up here in the return argument, the return value, and then we also return the location of the max over here. Now, why would you use, what are some of the reasons for using reference variables? Well, one of them is for being able to pass things in and out. The other thing is that call by value can be expensive. So let's say you have something that's very large, takes up a lot of memory. The last thing you want to do is to make a second copy of it. And worse yet, to make another copy of it that gets passed out via call by value. Because when you pass out a value, you're making a copy of it as well. So references and pointers make it efficient to pass very large objects into functions and pass them out again. Now, const makes them a little safer to do that. You can indicate whether they're input out only and not be modified. Now, shortly we're going to see you can not just return values, you can return references as well. But let's put that off. So here we start getting into why classes. Why do we want to have more types than what we have now? It looks like we have everything we need, or lots of what we need, certainly comparable to what we have in something like MATLAB. Very superficially. Is array the same as vector? Well, here's MATLAB constructing an array of length 5, 0, 2, 4, 6, 8. And I can just as easily construct, or almost as easily, construct an array of length 5 over here. So MATLAB and C can make similar looking objects. In terms of data, they're similar, but they're not functionally the same. Why? Well, look over here in MATLAB. I can multiply my vector by 2. Huh? This has no idea what that means. I mean, you don't even, it can't even make sense. There's no way it can make sense of the expression. There's no function that looks like 2 times float 5 and that being a binary operator. It's total nonsense. There are other things we can do in MATLAB. It's great. We can make matrices. We can multiply matrices. And yeah, we can make two-dimensional arrays, but they kind of don't do much. And well, things kind of, so this is actually legal. Notice we have This is 3 times 4 is 12. We're only setting the first 8 entries of this two-dimensional array. That actually is legal. The rest are defaulted to 0. Turns out. The way to think of this is that it's the, well, first of all, if you know Fortran, it's the opposite of Fortran. But the way to think of this is that for each, so A of 0 is an array of length 4. So as many years ago, and I was a graduate student here, John Kelly used to say, who was a chairman of the department, the math department, used to say, the only hard thing about linear algebra is remembering which ones are the rows and which ones are the columns. And he was absolutely right. I won't go that far, but certainly it is a hard thing to remember. We still can't talk about A by A. We still, A times A, we have, that won't compile either. We can't print F and A. You know, there's lots of things we can't do, and we'd like to be able to do. So what about 3D arrays? What about tensors? What about, you're not doing linear algebra, but doing something else? You'd like to have ways of managing the complexity of these things without writing out everything in terms of 1D arrays. So C++ lets you build user-defined types. They're referred to as a class. User-defined type is called a class in C++. Classes are a combination of member data and member functions. A variable of this type is referred to as an object. So if you have a class of type foo, then the things that you say foo, whatever is objects of type foo, or objects in the class foo. The class is the definition, is the type, and the objects are the variables of that type. Now, so classes provide a mechanism for controlling scope. You have different pieces of a class that are visible to at different levels. So you have private data and private functions. They're only things that can be used internally by the class. So if you have a class that's defined with a bunch of functions, you'll see that in a minute, then the things that are private can be accessed by those member functions of the class, but not by the outside world. Then you have, and the idea is that internal representations at some level don't matter if you have a consistent view to the outside world. Public data and functions are things that kind of present what kind of the real meaning of this class is. Just there's a sense in which, for example, for float, you really don't care to a large extent what the internal representation of a float is, what the IEEE floating point standard is. What you care about is what does arithmetic do on floats, and what rules does it satisfy. And that's the public face of float, is kind of given to you by what arithmetic does, what the functions do. And the internal stuff is stuff that you really don't want to know about. If everything's done right, you don't need to know about. Then there's an intermediate category, protected data and functions, closer to private than public. I think that in this class we will avoid the use of protected because we will try to avoid the use of friend functions, which are where they get used most often. So here's a little example, a counter. You want to have something that is kind of like, you know, the umpire's clicker, right? How many times have I done something? So every time you you're in a program, you want to know every time you've hit a location, you'd like to have a function that does that and stores it. So you have, here's a class counter, has 2 private members. It has my counter, which is the integer that says how many counts you've had. And it has 0 encounters. This is actually going to be a signed counter. You can increment it or decrement it by 1. So what are the member functions? You have a constructor here. You have an increment function, and you have a decrement function. And then you have something that can get you the counter value. So the function has as its data m underscore my counter, m underscore 0 counters. You're seeing, by the way, the first example of a coding standard that we will want in this class. Member data, so when you're referring to it in a program, will have the prefix m underscore. It's a convention. It's coding standards are agreed upon by people. They are not enforced by anything in the language, but it sure makes it a lot easier to read everyone's programs if you know how to identify member data. Mostly member data are private. They're the things that tell you what the internal representation is. The public interface is increment, decrement, and construction and get counter value. Those are the things that functionally counters, it's doing what counters is doing. So I can increment by 1, I can decrement by 1, I know what those things mean, I can find out what is my current value of the counter. So that's what counters, what? Yes? The last const. Yes, we'll get to that. I'll tell you what it means right now, but then I'll do it in more detail later. That last const says that when you call this function, it doesn't change the internal state. It doesn't change any of the data members of the counter. So we will see the use of const in multiple different places. So this is kind of a special case of a general rubric called object-oriented programming. Abstractions in programming are often described in terms of data and functions that operate on that data. So we put them, give us the ability to bundle them in the language. Lots of languages have this, and in some sense you can do object-oriented programming in anything, and even MATLAB. What are the benefits of kind of binding functions and data together? Well, the standard model for object orientation is that you actually have most of what you do is manipulating internal state with kind of a thin stream of data that gets it to talk to the outside world. That's not necessarily what scientific programming does. Scientific programming, you often bring state to a function and do something with it. You know, you're evolving something in time. The state has extrinsic value. So back in the early days of C++, everyone tried to figure out how to make everything look like objects. And it basically didn't work. However, all the mechanisms for abstracting things could be used in a much more flexible fashion, and the paradigm is useful, but selectively. So you have state. State has an internal representation. So the separation of internal representation, the control of scope, is something that's very valuable that you get kind of easily from object orientation. When you have things that are doing things to state, they may have internal state of their own. You're solving a PDE. The coefficients of that PDE may have an elaborate state of its own. The equation of state for a gas, for example. You don't, in some sense, need to see that for other parts of the calculation. So that can be internal state. So object orientation is a tool. It's not an answer. But it gives you some nice things. It gives you a way of making things modular. It gives you a way of kind of packaging things together, that's encapsulation. And a lot of this course is trying to explain what those things mean. So encapsulation is really controlling scope. Preventing people from setting internal data. In Counter, for example, having those two data members not be accessible to the outside world prevents you from, by accident, I mean, you're one programmer or someone else. This is a piece of code that's being used in lots of different places by lots of different people. You want it to have, you want it to have predictable and knowable changes to state. You know that the only way the state changes is when you increment or decrement the counter. If the data were accessible to the outside world, someone could grab that data and increment or decrement the counter without you knowing it, so to speak. Worse yet, if that data were a pointer, it isn't in the counter case, but it could be in other cases, and you'll see one in a moment. One could take that pointer, if it were accessible, and set it to another memory location. Have no idea. This isn't malicious. This is just things that happen when you're writing a large software system. You forget what it is you were doing and why, and then you take shortcuts. So this prevents you from allowing access to internal state that would completely corrupt the function. So the public part of the interface presents a contract to everyone who's using it, the programmer who built it and the people who are using a class. And the compiler, and the important thing is, since everything is known at compile time, you know what's private, you know what's public, the compiler will enforce a lot of that. Just as I said, if you know what's const and you try to make it not const, compiler will say, no, you're not allowed to do that. Modularity. So this is, so here the question is, how do you divide up work and how do you divide up what you see? So for example, in Counter, you know, the people who wrote Counter, the person who wrote Counter, needs to know what the internals are, obviously. They're writing Counter, they're saying what increment, decrement means. There are maybe a larger number of people who are using Counter in an essential way. And then there's a much larger group of people that just need to know Counter is doing its job correctly. And this modularity, which is what you get from control of scope and the various techniques of using const, such as using const, allows you to maintain the boundaries between these different functionality. And in particular, it allows you to it allows someone to, for example, change the way that something is implemented without changing its function. When you do performance engineering, as you will do a lot of if you take CS267, how do you build a high-performance piece of code? Well, often what you do is you think, well, I kind of know how to get performance, I kind of know how to build it, how to architect it, but I'm not going to really know the details until I build something and measure it. So how does that become a manageable process? Well, the interfaces to the code, the things that are the interfaces between you and the things that are going to have to be changed a lot to get performance, you try to make stable. You try to design them in a way that they won't change in kind of changing the code for the purpose of getting performance. And then that means you can go ahead and use it. You can use it in lots of applications. You can start seeing in the use cases that you have where the performance gotchas are, where you're not getting performance, and go change that without having to go change everything. This is what you really want to do with, this is why modularity is important in high-performance computing. Now, the trick is, of course, how do you decide where to put the interfaces? Where's the boundary? This course is taking a somewhat doctrinaire attitude towards this. The doctrinaire attitude is that the boundaries are given to you by the mathematics describing the algorithms that you're implementing. That's why the motifs. The motifs are a mathematical description of various kinds of algorithms. And in this course, in some sense, we use the mathematics of those motifs to define what the interfaces are. And then in kind of at the back end, we can do things to make the implementations go fast. And because the mathematics of the algorithms don't change very rapidly, we have a reasonably good chance of that being a relatively stable process. So let's walk through kind of a simple example of this. This is vector. So MATLAB has a vector type. Everyone has vector types or array types. So let's make one using class. So here is the first attempt at making a vector. So here is public. So what is this doing, first of all? This is defining what the class is. This is, in some sense, there's a whole bunch of stuff here that for a POD is just the statement, this is an int. So in defining a class, you have to define the functions in this class and the data in this class. So we have a bunch of functions. You have two funny looking ones. They're the name of the class and the name of the class with the tilde in front of it. Well, these are called the destructor and constructor. We'll come back to those in a minute. We have multiple constructors. Now we have a bunch of other functions. This is the signature of how you define a function, how you define what a function should look like. It is the return value. This is a special kind of function. It is an operator, and there are a special class of characters or sets of characters that are allowed to be operators. Equals, star, plus, plus equals. There are a bunch of others. Square bracket, round bracket. You're seeing several of them here. So these are all operators, and I'll show you how they work in a minute, but they take arguments. Now you have an ordinary run-of-the-mill function. You have norm, and then it takes a value as an input. And you have shift, which is move things over. And then you have finally down here private. Now, how do functions get called? Let's see what it looks like. So I've defined these functions. Just to keep you oriented here, you have, the functions abstract things in just the same way float, int, and double abstract things. We have a set of public functions that do a bunch of things. We have binary operators. We know how to multiply two things. It looks symmetric, but it isn't, and I'll show you what that means in a moment. And then we have some construction and destruction. So we have down here, there's a private section that shows how the class is going to be implemented. Now, there's a funny thing going on here. The size of the data for the vector, is known at compile time. What's the data? It's a pointer to a float. Pointers have fixed size, and it's an int. However, pointer to a float gives you the effect of a dynamic object, because what you can do is when you construct the object, you can give it a size and allocate that from using new. Got to be careful though, because then you're going to have to remember to delete, but this is going to give us a mechanism for handling that easily. So here's an example of using a little main function that uses the new class. So we have to communicate to our program what is this thing? What is vector? So all of these things that I just showed you give you a header file that defines what it means to be a vector. And so you put that header file in at the top of a program where the rest of the program can see it. Anywhere that's going to use vector can see it. So it has to be in same scope or outer scope relative to that program. Now here's an example of something where we need more machinery. So we need math functions here in C. So that's a way of getting access to those. So here we are, we're off. I'll set the number of cells to be some number, 11. I'll have a float that's equal to 10. And then here's the analog of int. Here's the analog of this statement up here, int cells equal 11. Here's the analog of that for vector. I've declared x to be of type vector, and then what is this doing? This is calling the constructor. This function up here, start, end, number of elements. So what the compiler will look for is it'll go up to the header file and say, do I have a constructor that has this set of arguments? If so, use it. Then I'm going to have another constructor that just says it's the number of cells, 11. And then I do some more computing. dx is length divided by cells. I set up to do, I have another float, which is m. So what I'm doing here is I'm filling in my array. I fill in x with grid points, if you like, one-dimensional grid, just equally spaced. And then I fill in u with sine 2 pi times m times the length, divided by the length. So I'm filling it in with some function evaluated at grid points. So what am I doing here? Where did x of I come from? X of I is this operator. So square bracket is an operator, and what does it do? It's returning not a float, it's returning a reference to a float. So I'll tell you what it's doing. It's taking the ith element in that array and returning a reference to it in a way that you can set that reference. So this is what you mean in the normal sense of the term by indexing an array. Indexing an array in a way that appears on the right-hand side takes an array, grabs the address of it, and presents it in a way that I can fill that in. And that's what, this is now where you start seeing why you need reference variables. You need them as return values, whether you're doing it in a left-hand side way, x of I, or you can do it in a right-hand side way as well. We'll see an example of that shortly. So u of I is this. So that's one example of the kinds of things you can do. This is of the functions that we're calling. These are member functions. Now, the operator square bracket has a very specific set of assumptions that it makes. Is that you give it the object name, square bracket, and one argument. You're only allowed to have one argument for square brackets. If you have round bracket operators, you can have multiple arguments. So there are various rules like this. Down here is a much more conventional calling of a member function. So norm is something that computes a norm of a vector. And what am I doing when I give object name dot member function name and arguments? That's calling that function on that object. So you can call norm. This, by the way, is what we're doing up here too. It's member function name, operate, and then a particular kind of function that we're calling. But the member function name always comes first. This looks like we're doing something different from that. U star U. We're not. This is an operator. U, the first occurrence of U is what you're calling it on. The second occurrence of U is the argument. So up here, if we go back to look at star, star took one argument, its vector. That's because the first argument, the first u, the first vector in the product, is the thing it's being called on the member function. So down here, if you were to say, instead of u star u, you say u star x, it would be the member function of u, and the argument would be x. X star u, other way around. It looks symmetric, but it's not. And in fact, there are kind of a number of annoying little things that you have to deal with. So it's easy to define algebra on vectors, because I can define, in fact, let's go up here. Here it is. Here you have star float. What does that mean? That means I can take a vector, star, a float. So I can do u times a. The thing I can't do as a member function is a times u. So in order to have real algebra where you're allowed to multiply on either side, you have to build a kind of mirror set of functions that say a times u is equal to u times a, instead of helper functions. Now, here's something to indicate what I'm not allowed to do. So float one value is to, so here's how you access data members. u.mdata is give me whatever mdata is, which is a pointer to a float, for the object u. And then that's a pointer to a float. It's perfectly legal to index it at 0. However, this is illegal. The compiler will say, no, you can't do that. And the reason is, mdata is private. In this scope, I'm not allowed to touch it. When I'm inside, obviously, I have to be able to touch it somewhere. When I'm inside of u, when I'm inside one of the member functions of u, I can access mdata. But I can't access it from outside. And this is an example of how you're being protected. So let's go ahead and try to compile this. And what happens is, now you're seeing examples of a couple of things. One of them is that, yeah, we declared the functions. We said, here's the class, here's what its name is, here are the functions on it, here's what their signatures are. Signature is a term of art. That's the name. That's a function name combined with the types and the list and types of arguments. But I haven't actually defined these functions, and the way that so at link time, what the compiler will come back and tell you is, I can't find this function. I can't find any of these functions. They're all referenced from main. So what we actually have to do is go back and actually define the functions. We declared what the class is, but we haven't defined the member functions. So vec1.h is called the declaration or a prototype, and we collect all of these in a header file, so that's hence the term .h. So everywhere where we use vectors, where we want to use this vector, we have to include this header file so that that procedure can say, okay, these are the functions I need in order to do this, and I will look for them at link time. I will know where to jump, what functions to jump to, because I will link to those. Now, there are some tricky business, which we'll come back to later, is that in a complicated system, you're going to have lots of different things that are using lots of different headers, lots of different ways and lots of different nestings. How do you keep things from happening more than once? Well, there's an easy way of handling that. But we also have to have one file that contains the actual functions themselves, what they do. And that'll be a .cpp file, and that'll be also compiled by the compiler. So here's kind of a couple of examples of what it looks like. You have, here's the constructor. This is, how do I build a vector? So first of all, what does a constructor look like in a .cpp file? This is something the compiler is going to compile. So I have vector : vector, Vector, the first vector here is saying this is a member function of the class vector. The second vector here is this is a constructor. So what do I do? So it takes an integer, and data is going to be new float of that integer. That's how big my vector is. Here, size is, I'm going to store that, and that's actually how big my vector is. I'm keeping that around. And now any further invocations of member functions on the object will have that data available to me. I know what data I've stored in that, and I know how to find it because I have a pointer to it, and I know how much of it I have. I know how long it is. Now, down here, you have vector tilde vector. That's the destructor. It does one thing. It calls delete. There's lots more stuff to go here. So this is going to be typical of what you see. So let me go over to somewhere else. Okay. No, that's not working for me. Let's go here. Okay, so this is a class you're going to see later on your first programming assignment. This is class you're going to be given. So this is points. So this is points on a dim dimensional grid. So on the left you see point.h, and so here are all the functions for point.h, and this is what things look like. The inline keyword is a hint to the compiler, which it's free to ignore, saying there's a more efficient way of compiling this than making a new function and having a call to a function. You can perhaps try to just expand this inline as part of the code, as part of the calling code. So ignore that, though. So you have a bunch of functions. Here's the constructors. And this is what the declaration looks like. This is what a .h file looks like. What does a .cpp file look like? So, and this .h file is going to appear everywhere that you use point. The .cpp file you will only make once. And it's actually, in this case, it's not a .cpp file. It is it's another .h file, and I'll explain why in a moment. But the important point is, whether it's another .h or a .cpp, what you will have is this was a bad example. Never mind. Let me get a better example up here that has a .cpp file. So let me go here. Yes, I wasn't thinking clearly this morning when I did this. So here's box. Here is, yes, so ignore that. So here's, again, it's another class. Box is just a rectangle of points. You have one corner, another corner. So this is what your .h file is, declares names. And here's what the .cpp file is. Now, everything that you want to indicate is a member function of this class, I'm calling it dbox, has a dbox : : so constructor, recompute size, these are all member functions. Now down below, in the same file where I'm computing, I have functions that, I can have other functions that are defined and declared over here, in fact, that are just useful to have. I have things that will print points. I have things that will do I/O. So you can mix things that are member functions and things that are not member functions in the same file to be compiled. The way it tells the difference is that you have class name : : for member functions. Okay, so let's go back. Oh, don't do this to me. Okay. So, so by the way, integers, all your PODs have these things. You're just not allowed to touch them. They're predefined. The other thing is that, so let's, go ask the question, what happens if, you know, here's our here's our vector class, and it was vector of floats. What happened if I wanted to have vector of doubles? What would I have to change? Well, I'd have to give it a new class name, because I'd have to be able to distinguish between vectors of doubles and vectors of floats. I'd have to give all these names different. I would also have to change the types. All these types here, the double, instead of pointer to float, I'd have pointer to double. Instead of return a reference to double. So yeah, you can do this. It has an ugly and derogatory name, cut and paste coding, and you can do it, but you shouldn't, because when you start doing things that are at all complicated, and you replicate them using cut and paste coding, and you find a bug in the new version, how many cut and paste versions are you going to have to trace back to fix that bug in all locations? So it's something to be avoided. And then there are other things. I mean, it's a maintenance nightmare. So this is why the idea of templates and generic programming came in early. So it was around actually before C++, but the developers of C++ saw a major advantage to this and latched onto it. So most languages have a mechanism to express a repeated pattern of code just once and let the language, the compiler, the runtime replicate the things that should be automatically replicated. The old name for this is parameterized types. So here's how it works. Here's vector now as a template class. So this is a parameterized type. Vector is a class. It takes as a template argument, which is this thing here, another class. So then when you actually instantiate this, when you actually create a vector, and you'll see in a moment, vector can be a vector of doubles, it can be a vector of floats, it can be a vector of ints, it can be a vector of anything, provided that certain conditions are met. And the conditions that have to be met is that when you implement these functions, that they have to make sense for the value of t that you've inserted. So, for example, you have to be able to call new and delete for t. You have to be able to call whatever it is that allows you to define plus, that allows you to define star times t, all these other things. So that's what the particular flavor of vector, but there are still lots of things that you can do this for. In fact, lots of arithmetic things that you can define vectors of. You can define vectors, if you had a matrix class, you could define vectors of matrices. So how would this look? Well, so we would have vector.h, a header file that had this in it, but it's going to have more, and I'll tell you why in a second. Here's main. Here is the same program we had before, except now instead of declaring something to be vector, it's now vector angle bracket template type. So this is, x is now a vector of floats. U is a vector of floats. And we can come down here and have our result be a vector of floats. These two things are actually defined and legal. Change it to double, that's what changes. And none of the implementation of vector, given what we have done, has changed. So we write it once for t, and it has to be there for all t. Now, where's the problem? I showed you a declaration of vector. The compiler doesn't even know that you need a vector of double until you start compiling that other program. In addition, there's no way of defining a vector.cpp file in the abstract, because you're going to do, for example, when you're multiplying two vectors, you're going to have to know what multiplication means, and that will depend on what your parameter is. So you can't have a vector.cpp of an abstract parameterized type T, because the compiler won't know what things to link to execute those instructions. So what C++ does to fix this is that the definition that is generic goes into vector.h. And that was the thing I got wrong. I put a point, and let me go back there. Come on. So let me put point back up. So here's what happens when you have either templated classes, or in this particular case, you have inline functions, is that you have the definitions, you have the declarations up here, the definition of the class, and what's defined on it. And then keep going, get to the bottom, and then you include the implementation here. And it's part of the header file. And now we go over here, and this is how the signatures, the implementation goes. It's assumed that this file, so these files here, you have some things that are member functions that have this signature, some things that are not. They're all down included at the bottom. So what happens is the compiler will include, let's go back. So the compiler will include vector.h, and then when vector.h is included, the compiler will then see, oh, down at the bottom it says include vector implem.h, and include that there. Now at that point, it has all the information it needs. It has the abstract version of the implementation of all the functions and the function headers, the declarations. Now the compiler sees vector of double. It knows what version of this to build. It knows what version of the constructor to build. It knows what version of these things to build because it has all the information. It knows it's a vector of double. Now here's another tricky bit of business. That's a relatively recent phenomenon. Originally, what the compiler would do is it'd see a vector of double and it would attempt to build all of the member functions. Well, it turns out that maybe you haven't, you don't have, you're looking at a vector of something that's not doubles that doesn't have a multiplication defined on it. Compiler would give you an error. Now compilers are smarter. If you don't use something that requires, if you don't use, say, for example, these two functions, what you really want is just a linear array of things as a container, it will not, for a templated class, it will not attempt to build them. It will only build the ones it needs. And that makes managing templated classes a lot easier. You can add capability to them for special cases, and it will be ignored for the general case. Or if you attempt to use it inappropriately, the compiler will tell you, sorry, no can do. So here's a simple example. You have the template definition, and then you include the, the implementation of the constructor. Now, here are all the ways you can use vector. We have vector of floats, vectors of ints. We have this. It turns out that there was a friend function that allowed us to do this. We have a vector of int. This is a copy constructor. This is another kind of constructor that I didn't point out here, where there's something going on here because this is a vector of floats. This now becomes a vector of ints that is defining the ints in terms of taking the floats and truncating them. vector of box. I showed you a box class here. What about this? I have a b vector times b vector. Does this even make sense? No, it doesn't, because the type of this thing is wrong. It is possible that b vector times b vector, a vector box times a vector box, could make sense. Depends on whether you define star. And there's a perfectly sensible definition of star that you could make. It could be the intersection of two boxes. Perfectly nice way of defining intersection. And then you'd have the intersection of all the boxes. But this looks like it's going to be wrong. And in fact, this one looks like it's going to be wrong too, because I don't think it'll do the type conversion. But if this were another infect, so if this had been res, this had been perfectly okay. This is a copy constructor. Standard template library. Vector's great. Saved me lots of coding. In fact, it's so great that it's just provided to you by the system. There's the vector class comes bundled with C++ already. I use this because it's an easy example to illustrate ideas. The standard template library has a lot of stuff in it. We will only use a relatively small subset of it. In addition to that, it's stored in the same place where a lot of other useful things are being stored. So here's a problem with using something like STL. I've defined my vector. STL has defined its vector. If you have two things with the same name, the compiler will complain. You can't have that. So how do you deal with that problem? Well, what you do is you can declare a library or a collection of libraries to live inside what is called a namespace. And there is a standard namespace, std, which contains STL, and it contains a bunch of other stuff. IO, for example, is in the standard namespace. And there are two ways you can use it. One is that you can invoke a member class of something in standard namespace by prepending to the name std : : so std : vector. Or if you're reasonably confident that you're willing to get rid of all collisions, which is not necessarily a bad thing, and you can do it on a kind of compilation unit by compilation unit basis, you can just put at the top of this scope in using namespace standards. So if it can't find a function, it will first assume, can I find the function by saying it's standard, it's std : something, and then look at the header files I've included up here. And so this now becomes a perfectly legal way to use STL vector. It's the same program we wrote before, except down here we run into a problem. The vector in STL is a fairly general one. It decided, in designing this, it decided, no, we don't need vector operations with multiplication and stuff like that, because we're using vector as a general container. We may have vectors of pointers where multiplication of pointers doesn't really make sense. So down here, we commented out these two lines because they wouldn't have made sense. However, we can always write another set of functions that are now kind of helpers that will implement those. We'll implement x times x. That will take a vector of double times a vector of double, or a vector of anything times a vector of anything, and have it be templated on that, and only use it where it's valid. So there are lots of ways of extending STL so that it actually meets all of our needs. Here's another example of doing this. The only thing I want to talk through here, this is manipulating, so this is using a couple of things in STL or in the standard namespace, one of which is string, which is, I believe, is an STL. And the other is IOStream, which is not really a standard template library, but it is a very nice way of doing I/O. It's much better than doing printf because it does the formatting for you, among other things. So here's how streams work, is that cout is the standard output to printer stream. Cin is the standard input stream to from printer. So here's how you output something. Cout greater than something, and then endl is end of line and flush the buffer. So it makes sure that everything there got printed. So what is this greater than? Cout is a stream. It is a special name for the stream that goes to your terminal, goes to your screen. However, you have to define functions that do the right thing. So here is the class of functions you define for doing I/O. It is a template class. It takes, because we're using vector of template, and it's going to take operator greater than or greater than. It's an infix operator that is an operator on O streams, on things like Cout. Cout is an O stream. And it takes O stream and, it takes an O stream, and it's a thing of type vector, and it produces an O stream. This is the type of the output, is O stream. It's a reference to an O stream. So let's go back to what this is doing here. So if I had wanted to string these together, Cout greater than strings, greater than strings again, or another string, or something of a different type, and then on and on. What this binary function does is it takes this and does something to it that eventually will cause it to be printed at the terminal, at the screen. And then it returns as a return value Cout again. So it's ready to have something else sent to it. And how do we build these things? Well, we build them up by, here we're doing an output stream by saying, let's go through the vector, and for each element of the vector, we send this to our stream, to our input stream, and just keep going. So at some point, then you have to have, well, my type T then has to be defined on, have a stream output defined on it. Well, you can do that. You figure out how to do that. But eventually you get down to plain old data, to PODs. PODs have the operator greater than predefined. So outputting integers, floats, doubles, easy. There is a version of this for input, and there's also a version of this for file input and output. All these things are very useful. And as I said before, here's the take the sum of the product, take the dot product of two vectors. So here's a templated class, and we can write that and put it in our header. Put it in our header file. And it does what you would expect it to. Now, unless you actually use this for this type, it won't get implemented. It will not be compiled. It will only be compiled for the thing. So if you use it for double, it will be compiled and correct. If you have a vector of something else, of pointers, and you don't ever use this, nothing will happen. It will still compile correctly. If you have a vector of pointers and try to use this, the compiler will complain because there is no product, there's no infix star defined on pointers. And this is the thing outputting our string. So let's come back to const. Const is, for classes at least, is a little easier to keep track of, and it's partially because I do it a lot. So const can appear multiple places. Someone's already asked about this, in a member function. So here are three examples. Here we have a member function foo, or a member function bar, that's a member function of class foo. It takes as an argument a vector, a const vector of, a reference to a const vector of inst, a const reference to a vector of inst. And then we have these two, and it returns a reference to t. And then we have these two other consts here. So what are these consts doing? So first of all, here's a return value. But it's not a value, it's a reference. It's something I could, in principle, write into or access as if it were I was getting that value. The const says you're allowed to read it, but you're not allowed to write into it. So that says, in particular, that I couldn't put this on the left-hand side of an expression and assign to it, even if I had a legitimate, the compiler will catch that. Here's the other instance of const. We're inputting const here, and we're not using it. We're only reading it. We're not writing into it. That's what this is enforcing. Now, this sounds kind of silly, right? Because you have a const there, the body of the function's in front of you. Why would you worry about this? Well, the reason is that this body of a function may call a bunch of other functions. And if const doesn't get propagated correctly, if at some point you pass it to a non-const function, the compiler will complain. And you want that to happen because you really do want this not to be changed. What about this const? What about this final const here? This const tells us that the object of this class, the object of class foo, that is calling bar, this function here doesn't change the state of that object. And again, why would you care about that? Well, if your object had been declared to be const in the calling scope, and you want to call this function on it, this guarantees that that const won't be, that's legal. If that const weren't there and you had declared something to be, you declared something of this class to be const in the calling scope, it would get it wrong. The compiler would say, no, you can't do that. That is a function that could conceivably modify the state. So getting these const things right, even though they seem to be initially a little bit redundant or superfluous, it really eliminates a lot of problems, and it also forces you to think clearly about, okay, what do I really need to be modifying here? Don't make everything non-const simply because it's convenient. So there's one other thing. Const is part of the type system. Remember, I keep saying that. That means all of these consts in here, this particular function here, I have another function down here without a const in the reference. That's a different function because the return type's different. Now, this kind of overloading, you're allowed to overload. You're allowed to overload function names as long as the types are not ambiguous. So it's allowed to have a bar with a different type, return type, same name, same arguments, but a different return type. And const is enough of a difference. Now, compilers sometimes will choose the wrong function and give you errors, and then you kind of got to you have to work on it to force it to do the right thing. However, there are cases where you really want to have both of these. Because, let's say again, think of the array example. The array example, you want to be able to index into array and use it to build right-hand sides. That's a const operation. So you definitely want the const version because that'll preserve constness. On the other hand, if it comes time to actually assign a value, you need the non-const version if you want to assign into those values. So you need both. By the way, you should look up L value and R value. They're more or less what you think they are. Things that appear on the left-hand side, things that appear on the right-hand side. Let's see. We're almost done here, so let me go to the summary. I'll pick up that last slide at the next time. So summary is classes are user-defined types. There's a combination of member data and member functions. They control scope through public, protected, and private. Member data is always a fixed size with the runtime sizing of data mediated by pointers and memory management. So the reason I keep emphasizing this is that there will be points at which you will see kind of funny things happening that look artificial. But a lot of them can be traced back to the fact that at the end of the day, the only way you get dynamic things is via the memory management, the memory manager, is via new and delete. And that imposes some, and everything else is all of the data members are of fixed size and known at compile time, It gives opportunities, but it also imposes constraints. What we're going to see from this is the power of composition. We're going to build up more complicated classes out of simpler classes. Data members can be not just POD, but they can be other classes. And the structured grid example, you will be given the first couple of classes and asked to build the third one. And those first couple of classes will be built out of POD, out of STL. You're already going to see that. Template classes, template parameters are completely defined at compile time. Integer, you can also parameterize by integers, by the way. So if you wanted to have, like before you were seeing things in point and box that were the dimensionality of the problem that can appear as a template parameter, or could have appeared as a template parameter. Those are allowed. You can have integers as template parameters, not just classes. But they have to be known at compile time. These are particularly good for collections. Many operations on arrays, lists, don't depend on what the list elements are made up of. Standard template libraries gives us lots of stuff. And by the way, we've used lots of things from the standard namespace in these examples. Vector, IOStream, CMath, which is where math is. I didn't talk about CAssert. It's a way of catching bugs when you're not ready for doing full-out high optimization. And then, of course, some very nice string manipulation things. We will be using things in the standard namespace a lot throughout this course. Okay, so that's it for today, and I'll see you on Tuesday. Now, I'm hoping by Tuesday, please, everyone, send in your SSH key to Max, because we need that to set up the Git repositories.